Hello, my name is Bruce Kranhoff, and welcome to my third screencast on quantum computing. This one is following lecture 4 of a course, some course notes, and it covers quantum teleportation and Dutchess algorithm. This screencast is meant to be complementary to the material itself. I've got links here, and it's meant for somebody with a similar background to mine. So, this is the third screencast, as I said. It covers these lecture notes. So basically lecture 4. We're going to look at quantum teleportation. This uses pre-entangled bits and then uses that to transmit an actual quantum state. And we're going to look at Dutchess algorithm. So we're actually going to look at, if we have a bitwise function, how do we actually implement that? And then, given that we can implement that, how can we in one operation figure out whether it maps to just a single bit or to 2 bits? And as usual, I may use this special notation rather than writing out that normalization term. Cool. So, quantum teleportation first. Let's go over the protocol. Here it is. So, what we have here is we've got psi, which is an input state, and then we're inputting the single state phi in 2 places, which means they're totally entangled to start with. Okay? And then what we're going to do is we're going to do a knot here. So if psi is 1, then we'll do a knot on this version of phi. So now this version will be different than that version. And then we'll do a Hadamard on that, and then we measure them both, so it collapses to one of the possible states up here. We transmit this, over fiber optics or wherever, to somewhere else in the world, where they still have this other qubit, which was entangled with the original one here. And then we do a knot, a controlled knot again. If it's 1 here, we do a knot on that qubit. And then if this is 1, we're going to do a negative here. If it's 0, we don't do anything, and then psi will end up, like what we get out here is actually psi. It's precisely this state. It's pretty cool. So we're going to look at how this works, and then kind of the underlying ideas. So to start with, this state and this state are totally entangled, right? And so that's why we're either in 0, 0 or 1, 1 for the second 2 qubits, because they're exactly the same. And then the first qubit can be in some arbitrary state. So that's why we've got our arbitrary alpha and beta. And we could expand this out and write it out like this. Now, after we do a C0, the second bit, because that's the one we can change here, the second bit will change if the first bit is 1, right? This is a controlled knot. And so these won't change, but here these 2 will change because the first bit is 1, so that'll become a 1, that'll become a 0. And so that's how we end up with this. And these are unchanged. Now, so far this wouldn't be that useful. If we measure these 2 bits here, the first 2, then we know, okay, this bit here has to be 0. There's no kind of quantumness left. It's totally determined. Similarly, if we measure 0, 1 for these 2 bits, we know that the third qubit is in state 1. Same with this. We know it's in state 0. Here we know it's in state 1, right? So basically the first 2 qubits occur in each state only once. So if we measure them, the system's fully determined. So we don't want to measure them yet. Now the second and third states, they're all distinct, right? 0, 0 for the second and third, 1, 1, 1, 0, 0, 1. Those are all distinct, which means now if we do a Hadamard on the first bit, this state won't somehow get mixed up with any of the others because the second 2 qubits make it distinct. So if we do a Hadamard, each of these states will split into 2 states and we'll end up with a superposition of 8 states. Then when we measure 2 qubits, that will collapse us you know, when we measure 2 qubits, that means 4 states collapse down to 1, but we're still left with 2 states, right? 2 out of the 8. Yeah, when we measure. And so having 2 states left over, that might be enough for us to transmit the quantum state. All right, so next we've done the controlled knot here. So next we're going to do the Hadamard. And there we go. Okay, so we do the Hadamard. We get this state. So now what we're going to do is we're going to take out after we have in this form, we're going to take out the first 2 qubits, because those are the ones we're going to be measuring. So we get it in this form. And so we see here, once we measure the first 2 qubits, we're still left with a quantum state containing alpha and beta. So if we measure 0, 0, you know, by chance, then our quantum state will be, this would be exactly psi. If we measure 0, 1, which happens a quarter of the time, because, you know, 1/4 squared is the probability, then, well, our probability of being in state 1 is alpha, not beta, right? So that's a bit different. And our probability of being in state 0 is beta, not alpha. So these are switched, right? So to get back to the original state, we need to flip those. Well, we know how to do that. That's a not operation. If we happen to measure this state for these two, then we're left like this, which is almost psi, except we've got a negative sign. So we know the sigma z, like the Pauli Z spin matrix, it can flip this back. And here we need to do a not, and and then, because of the negative, we need to do a Pauli spin matrix thing. Yeah. Okay. So this is looking hopeful. So at this point, we do actually take the measurement. So it either collapses to one of these 4 states. Notice that the 3rd qubit here, we're not measuring that. So the 3rd qubit stays uncollapsed. That's important, right? Cool. And then, so I was just going over here. If the first 2 qubits collapse to this measurement, 0, 0, then this 3rd qubit, psi, actually I shouldn't call this psi. I should call this, we want this to end up being psi, but this is really qubit 3. Is in these states. So first of all, let's say, okay, we've got beta times state 0. We want beta times state 1 actually. So here we need to flip the states. Similarly with here. Okay, so we need to flip the states when, looking over here, it's when the 2nd qubit is 1 that we need to flip the states. So really we can just do a controlled not on the 3rd qubit using the 2nd one, which is what we have here. Okay, so that'll flip this, and it'll change this to a 1, it'll change that to a 0. So now this state will become the same as this state. Maybe I can insert. So after we've done this, this became state 1, this is state 0, that's state 0, that's state 1. Okay, so now we still need to flip this sign, and we know what operator we can do that with, the Pauli spin, or sigma, the Pauli Z spin matrix. And we need to do that in a controlled way, right? We don't want to do that here. We do want to do that here. So we look over here and we say, oh, the first qubit is 1 in those two, and the first qubit is 0 here. So we can do a controlled spin Z, controlled like Z sign flip, which is one of the gates, one of the possible gates. And so we apply that, that'll flip both of these, and then all of the states will be like this, which is just the original psi state. And there you have it. That's the algorithm. So a question I had was like, so how does this actually work, right? How is this quantum state actually kind of transmitted? It's not totally transmitted, because remember, these two are entangled. We're using that, and then we're also using this extra information. Well, my understanding of this is the transmission of the state really has a lot to do with that we've actually made the measurement, which collapses the wave function, right? And we modified the states here before we did the measurement so that it would collapse in the right way, right? So then we were most of the way there. And then we just had to use a little bit of information here to, modify these to get this into the state we wanted. But mostly the collapsing made it pretty much psi already. And remember, collapsing a wave function, another way to look at that is that we, the observers, are becoming entangled with a quantum state ourselves, so that we observe, in our entangled state, we can only see one of the collapsed quantum states, right? So by taking the measurement, we entangle ourselves. By sending this measurement over wires and whatnot, we definitely make sure that whatever is happening over on the other side is also entangled in a quantum way. So therefore, they will observe stuff as though they're entangled or as though it's measured. Cool. Yeah, so that's my high-level understanding of how this works. So basically, we needed to do a C0 so that we made the second states, the second two qubits all distinct. Then we can do the Hadamard, splits into 8. Then we can measure, and we still have the 2 states left. And then with the right flipping, we can get it back to psi. The path not taken. So this is just like trying to think of, why didn't we just apply the Hadamard? Why did we need the C0 in the first place? So if we applied the H right away, we start out in this state, right? And so the second two qubits are either both 1 or they're both 0, right? And so then when we do the Hadamard, this state here and this state here will mix up, because this 0 will become a mix of zeros and ones. And, sorry, hold on. Yeah, let's look at the starting state. Yeah, after the Hadamard, this state and this state will become mixed up, which is why this starts out at 1, so it'll be alpha plus beta when those mix up, which is what we get here. And then when we flip this to 1, that's positive. When we keep this as 1, the Hadamard gives us a negative, recall. And so, so there we get the alpha minus beta, times that with a 1 there. And similarly for the other two qubits. And so we've only got 4 states, right? And so what happens when we measure the first two? Well, if it's 0, 0, we know the third one's going to be 0, because there's no other 0, 0s, right? So we've totally determined this third quantum state here. So we can't do anything with this entangled state now, because all the information, we already have all that information once we measured qubits 1 and 2. Cool, so that won't work. We need to do the C0 first so that the Hadamard states don't combine, and therefore we still have we don't have all the information about this state. Yeah. All right, so that is quantum teleportation. I'm guessing this is not actually used at this point in time, because somehow you have to entangle these, which you can do on a quantum computer, and then you have to transport it without it, interacting with the world and whatnot. And, the idea is that this happens a long time before, so this is actually useful. But, I think we can't perfectly isolate our, our super cold quantum spins from the environment. We make it super cold, we probably have vacuums, and I'm not sure about the details, but we try and isolate as much as we can, but still there's a little bit of interaction, and so over time the states become entangled with other states, and so we can't kind of sustain an isolated quantum state for that long, I don't think. And so I think this is totally impractical in practice, but interesting theoretical exercise to help us understand quantum computing more. Let's move on to Dutchess algorithm. All right, so basically what we're going to be working with is bitwise functions. So feed in a 0 or 1 and we're going to get out a 0 or 1, right? And so there's 4 possible bitwise functions. Feed in a 0, you get, if you feed in 0 or 1, you get 0, 0 no matter what, or the identity, or here's, what's this? You just flip it. It's the identity with a naught, or they all both map to 1. And for Dutchess algorithm, our objective is to distinguish the 2 in the middle here, where we have a 0 or a 1 as an output, from the functions that are just constant functions. Here we always output 0, here we always output 1. So the answer we're looking for is, it's a constant function or it isn't, right? And we're just going to try and do this with a single evaluation with a quantum computer. Now, of course, with a classical and therefore the quantum computer, we could do 2 evaluations. Plug 0 into your function, plug 1 into your function, see what happens for both of those, and then you know what function you have, right? This would be a lot more useful if you have, instead of a single bit, if you're looking at 20-bit functions or 20-bit to 20-bit or whatnot, then there's a huge number of combinations. So if you can look at a whole bunch all at once, that would be very useful, right? So first of all, how would we actually calculate a bitwise or a binary function with a quantum computer? So we can't take a single qubit and map it to f of itself on a quantum computer, because this is not it's not a unitary transformation, right? Unitary transformations should be reversible. They should preserve probability. This does not do that. Why? Well, an obvious reason is f0 is mapping both of these states to state 0. You cannot reverse this operation, right? You can't go from this back to 0 and 1, right? You don't have that information anymore. Okay, so it's not reversible, therefore we cannot do this on a quantum computer like this. Also, you could imagine if something's in a superposition of state 0 and 1, there's an alpha and a beta. If you map both of those to 0, then you've got like alpha plus beta in state 0, which if each of them is 1 over root 2, those don't add up to 1, like it's not normalized anymore. So we can implement this function by using another qubit. So we feed in 2 qubits, and for A, we're just going to take f of A, and then we're going to do the XOR operator with B. So if f of A is 1, we're just going to flip qubit B. We're going to do a not on qubit B. If f of A is 0, we're not. We're just going to leave B unchanged, basically. And so we could feed in a bunch of states. We could choose the second qubit to be 0, right? So I'm going to pay more attention to the bolded ones, the bolded rows here. And so for each of these functions, yes, that's not possible. Okay, so for each of these functions, if we put a 0 in, the first 2 are 0, the second 2 are 1, so these stay 0. The second 2, we flip the second qubit, right? Similarly for this, the first and third should stay the same, the second and fourth should flip, and okay, first and third are the same, second and fourth become 1, 1. So yeah, so this is how we might, and then you can see here the second the second qubit here is just the second value here, and this, oops, and the second qubit here is the values here, right? Cool. All right, so we can, this way we can do this function, and then we could measure qubit 2, and we could get the output of the function, right? Now, doing this is a unitary transformation. It is reversible. It's easy to see that it's reversible because some of the time we're flipping the second qubit, right? And if we just do that again, right, then this state would go back to 0, 0, right? So we can reverse it. Similarly, we flip the second qubit here, or let me see, this one wasn't flipping, so if again we don't flip it, it stays. If again we flip this one, then right. Yeah, if again we flipped this one, that would go back to 1, 0. Yeah. So this is actually a Hermitian operator. Yeah, it's unitary, it's reversible. All is good once we do this. Now, more generally, we might have functions from multiple bits to multiple bits. And so then we're just going to do something similar. We're going to take, so here, state X represents, a bunch of qubits in there. There's a bunch of qubits in state Y. We do this operator to it. It doesn't change state X. And state Y becomes the XOR with the result, f of x. Cool. So this is how we do this in general, but for Dutchess algorithm, we're going to stick with the single qubit and a single qubit being flipped. We're going to stick with that. All right. So the circuit looks like this. We're going to do Hadamards. That puts them into a superposition of all states, except here we've got a 1 going in, so we're going to get a negative. For when qubit 1 is in state 1, we're going to get a negative. We put it through this operator here. Right, we put it through this operator. Then we're going to do a Hadamard on the first qubit and then measure it. And the second qubit we don't need. The first qubit has the information we need. Now, you might want to go over the lecture notes first, because I'm not going to go into so many details as they go into here. Or you can watch the video first, but maybe it would make, if it doesn't make sense, read the lecture notes, then come back and look at this, because I'm going to try and give some like the higher level understanding that I got after I had gone through the details. Cool. So after the Hadamards, we're in an even superposition of all the states. We have a negative here because we initially put in a 1. Now we can partially expand this. So we leave the second part the same. We just expand the first part. And so it looks like this. And now for this second part, we know that some of the time we're basically, when you do an XOR, that's basically a NOT operation when f of a is 1. When f of a is 0, it does nothing. Okay? So what would happen here if you do a NOT operation just on this part? Just maybe pause it and think about that. Well, what would happen, this would switch to a 1, this would switch to a 0, and so now your 0 state has a negative in front of it, your 1 state doesn't. So you basically get a negative multiplied by this whole state. We could factor out that negative out front here. Similarly, if we do a NOT on this, it's the same as factoring a negative out. Cool. So doing a NOT, which is the same as doing the XOR when f is 1, basically just gives us a negative sign out front. So that's interesting, because we're doing the NOT on the second state, but then we get a negative sign out front, which is like we get a negative in front of the first state. So this is called the phase kickback trick, I think. And so let's look at this in more detail. let's look at this in more detail. Cool. So if we're working with function f1, so f1 is just the f1's just the, what is it? The identity. F1 is just the identity. So that means if we're in state 1, we're going to flip state 2. If we're in state 0, we do nothing. Okay. So we're going to do nothing with this. With this one, we're going to change the 0 into 1. We're going to change the 1 into 0, which ultimately gives us a negative sign out front, right? Okay. So now we've got a negative sign out front here. These and these stay the same, so we can now factor that out. Okay, so we get that out front, and this now has a negative sign, so we have this. So we're pretty much the same as we were here. I factored out the 1 over root 2's into a 1/2. We're pretty much the same as we started out, except we've got an extra negative sign there, right? Now what happens when we apply a Hadamard to this with the extra negative sign? It goes back to state 1, right? Okay. So when we do a C0, which is like F1, it just flips these two, which is a negative sign, which flips this to a 1. And so that's basically the trick. Similarly, if we used F2, then we would have flipped this one instead, and we wouldn't have flipped that one. So then we would have gotten a negative here and a positive here, which is just the same as this with an extra negative out front. So the Hadamard would still take it back to state 1, but with a negative phase in front. If we used F0, it makes no changes. So when we do the Hadamard, we just get back to the original state 0. If we had F3, which always outputs 1, then we flip both of them, right? So we get a negative sign from that, a negative sign from that. So overall, it's just like a negative sign out front without a negative sign here. And so we just get a phase shift, and otherwise we stay in state 0 after taking the Hadamard back. Cool. Yeah. So that's how Dutchess algorithm works. So the key ideas are we put this through the Hadamard, which gives us the negative here. With the two states negative, now when we do a controlled NOT of some sort, when we do a NOT for some reason, because a controlled NOT, or we do a flip because of an XOR of a function or whatnot, these two basically switch. This becomes a 1, this becomes a 0, so we have a factor of a negative, and that's the phase kickback, which goes back to the first qubit. So we get negative signs on the first qubit, and then the Hadamard, when there's a negative sign, it goes back to a 1 instead of a 0, right? It ultimately results in a flip in which qubit the Hadamard goes back to. And we may have a plus or minus in front, which doesn't matter. When we measure it, we're going to get the same value, because the probability of being in state 0 is still 1 here. The probability of being in state 1 is 1 here. Cool. So we just measure the first qubit. All right, hopefully that all made sense. Again, I recommend going over the lecture notes first for the details, and this may give you some more high-level insights after that, if it didn't already make sense. Thank you for watching.